Okay, today we're going to talk the chain rule, which is one of the greatest function or derivative shortcuts we're going to have. So far we've done derivatives of products and sums and power rule and such, but we haven't done anything where we have a function within a function. There's an example right there. X squared plus 1 is within the sine function. We haven't been able to do the derivative of that until today. In order to do that, and to understand where the chain rule idea comes from, let's first talk about a few chains or chain of events that we deal with. For example, unit multipliers. If I converted 2 meters to inches, I use unit multipliers in a way that meters doesn't relate directly to inches, but meters relates to centimeters, and centimeters relates to inches. And so by using that middleman, I'm allowed to make the conversion. So that, also known as the whoopsh, 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 whoopsh effect, gets us to inches. Same with that whoopsh on a fraction case. I can whoopsh, 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 whoopsh. Denominators and numerators that are the same, giving you 3/13. That whoopsh is about to happen in the chain rule. So here we go. Getting back to that derivative of sine of x squared plus 1. It's obvious that it's going to have something to do with the derivative of each of the terms. I know it'll have something to do with sine's derivative and x squared plus 1, but how does it work with those two derivatives? It's easiest to, at least the first time, and see how the chain rule works before we develop a shortcut, to break it into pieces. So I'm going to take sine of x squared plus 1, and I'm going to make the x squared plus 1 the inside. I'm just going to call it u and break it into sine of u, where u is x squared plus 1. And I'm going to find the derivative. Now, by breaking it into pieces, it'll allow us to see how the chain rule works. We're going to set up a chain of events. Now, I know now the problem is that when I say dy dx, I want to see how y changes with respect to x. Now that I've incorporated this u here, y doesn't relate directly to x, kind of like above how meters didn't relate directly to inches. We're going to use a middleman of u here. We can look at how y changes with changes in u, and then multiply that by how u changes as x changes. And by doing so, we'll talk about how y changes as effect of changes in x. That's pretty wordy. In symbols, then, it would be something like how y changes because of changes in x, or with respect to changes, or in u rather, would be dy du. And how u changes because of changes in x, that would be changes in u with respect to x, so that's du dx. Well, a lot like we talked about above in the whoopsh whoopsh section, the du's knock each other out, and we get a direct relationship of how y changes with changes in x. So for this problem, if I say, what is dy du, given that y is sine u, then dy du is the derivative, cosine u. And dy dx, given that u is x squared plus 1 for this problem, the derivative of u with respect to x is 2x. Now that is the derivative, and we just did the chain rule, but there's one thing wrong, and that is that our derivative is in terms of u and x. The original problem, before I made that substitution, was just x, not u and x. So the last thing I'm going to do is fix that u and replace it with what u equals. If u is x squared plus 1, then I can write my final answer as cosine of x squared plus 1 times 2x. And that is the derivative using the chain rule. Now, if we were to skip this u step and look at this, step back and look at this, what we just did, then we could say that when y is sine of x squared plus 1, the derivative was cosine of x squared plus 1 times 2x from what we just did. In words, then, we could say when we have a function within a function, we first had cosine. Now that's the derivative of the outside function in the original problem. And that x squared plus 1 is to say the inside stayed the same. Then we multiply by the derivative of the inside. That's where 2x came from. It came from the derivative of that inside x squared plus 1. That's the chain rule. You really take the derivative of the outside with the inside staying the same, and then multiply that by the derivative of the inside. It's pretty wordy, as I said, so the symbols make it a little clearer. If h is defined as a composite or a function within a function problem, that's when we use the chain rule, is when we have a function within a function. Then the derivative of h would be the derivative of the outside, which is f prime, with the inside g still in, unchanged. Then we multiply by the derivative of the inside, and that's why that g prime is there. So looking at what this looks like then in action here, without the u step. If I have, in this example, the function is e to the x squared plus 2x, and I want the derivative, to do this chain rule stuff, at the start you're going to have to give some thought to what's inside outside first. I think you'll agree that the e to the is the outside function, and the little piece that's in it is the x squared plus 2x. So when I say the derivative, the chain rule, is the derivative of the outside, it's the derivative of e to the. Well, I know when I take the derivative of e to the anything, it stays e to the. The inside stays the same, so the inside stays x squared plus 2x. Then I multiply by the derivative of the inside. The derivative of the inside is the derivative of x squared plus 2x. So that's 2x plus 2. That's my answer. That's it. Derivative by chain rule. Derivative of the outside with the inside the same times the derivative of the inside. I had an example or two for you to try in class, but we'll see how you do on the homework. Let's jump to another case here. Actually, this one is for you to try. I'll give you a second to try this. Go ahead and pause this if you're listening to this video at home, and we'll go over it in a second. Okay, so here we go. The derivative of the log expression here, the log is outside, the x squared minus x is inside. So the derivative then is the derivative of the outside. The derivative of log is 1 over what's inside. Then I take that and multiply by the derivative of the inside, which is 2x minus 1, power rule and all, and there's my derivative. Did you get that? Good. Okay, so sometimes the easiest ones are really the hardest ones. The ones that are missed most are problems like this one, y equals e to the negative x. And the reason is it's so clean, people forget they need to use the chain rule. It doesn't even slap you in the face with, yes, this is a function within a function. But it is a function within a function. You do need to use the chain rule. When you do the derivative on that, the derivative on the outside, the e, is the derivative of e, which is e. Inside stays the same, but then don't forget to take the derivative of negative x. The derivative of negative x is negative 1. And so you would get negative e to the negative x for a derivative. Don't forget to use that chain. All right, so those are analytical derivatives. Now let's use the chain rule as applied to table and graphical kind of problems here. Say I gave you this table of f, g, and f prime and g prime values at 0 and 1. And I asked you, given a composition, f of g of x, find the derivative at 0. First, give me the chain rule. The derivative of the outside, f prime, with the inside, g the same, times the derivative of the inside is g prime. Now I'm going to evaluate that at x equals 0. F prime of g of 0, I'll do in a second, and g prime at 0. Let's work inside first. G at 0, according to the table, g at 0 is 1. G prime at 0, here's g prime at 0, that's 1/3. And now we need to put 1 into f prime. 1 into f prime is negative 1/3. So I multiply that together and I get negative 1/9 for my answer. Do you see where I'm coming from? Try 11 on your own. This is 11 on the homework. So if you have the homework paper, then go to a number 11 on the homework and try this one using that same table. All right, pause if you need another second, but I'm going to go on to that. If I use the chain rule on this, then the outside is to the negative second. So when I take the derivative of the outside, it's negative 2 comes down, and I drop it by 1, now to the negative 3. The inside stays the same, g of x plus f of x. Then I multiply by the derivative of the inside. Derivative of g is just g prime. Derivative of f is f prime. Now I need to evaluate that at 1. So this would be negative 2 over g of 1 plus f of 1, and all that cubed, n times g prime at 1 plus f prime at 1. Plug it in from the table. I get g at 1 is negative 4. F at 1 is 3, and all that's cubed, times g prime at 1, which is negative 8/3, and f prime at 1, which is negative 1/3. Simplifying that, talk a negative 2 over negative 1 cubed times negative 3. Altogether then, that's 3 negatives, and so I get a negative 6. How'd that go? Hope you got that. If not, come in 7th hour and ask me. Moving on to a graphing case here. Say you were given graphs and you wanted to use the chain rule. H is a composition, so the derivative of H is f prime g stays the same times g prime. Derivative of the outside with the inside the same times the derivative of the inside. So at 4, h prime at negative 4, f prime at negative 4 is f prime at g of negative 4 times g prime of negative 4. Now, when I go to evaluate a function, I look for the y value. So g of negative 4 is find the g graph. That's here. Negative 4 is 2. Now, when you evaluate the derivative at a point, you're saying the slope of the g graph at negative 4. If I look at negative 4 in the g graph, the slope there is negative 1. Now I'm going to work on the f prime. F prime at 2 means the slope of the f graph at 2. Here's the f graph. At 2, it's going down 1 over 3. So that's a negative 1/3 slope times negative 1. My answer then is 1/3. Do you agree? Good. Okay, then. Last but not least, using a chain rule with a relative maximum. So we've been doing this this week, relative max. I want to start by finding where the graph goes flat, because that's a candidate for a min or max. Now, a graph goes flat if the derivative is 0. So I'm going to find where g prime is 0. And then after that, I'm going to sign test around the g prime equals 0 to see if g prime is positive before and negative after, indicating that g was increasing then decreasing, so I get a max, or was around my my derivative equals 0 point was g prime negative, indicating g was decreasing, then positive, indicating it went increasing, g went increasing. So I had a min. That's my plan, and then I'll make a nice conclusion with the first derivative test. So we need the first derivative first. That's where the chain rule comes in. If the function, rewritten as 4 minus x squared to the 1/2 is differentiated, or we take the derivative, then g prime is 1/2 4 minus x squared to the negative 1/2. That's the derivative of the outside with the inside the same. Then the derivative of the inside. The derivative of 4 is 0, minus x squared's derivative is negative 2x. Now, when I was doing the chain rule before, I didn't really clean it up. I didn't need to. But now, because we want to find where this is 0, we might clean this up. I could rewrite this as 2 root 4 minus x squared in the denominator and negative 2x in the numerator. I want to know where this is flat or 0, not undefined. So I am not going to focus on denominator zeros. I'm going to strictly focus on where the numerator is 0, and that is at x equals 0. Now before and after that point, I just found where the graph of g goes flat. It has a horizontal tangent. Before that point, if I put in maybe -1, then I would get -2 times -1, which is +2, over 2 root 3. Now altogether that's positive. If g prime is positive, then that implies g is increasing up to the point where x is 0, where the derivative is 0, so the graph goes flat for g. After that, after 0, say 1, I get -2 times 1, which is -2, over 2 root 3. That's negative. That means g is decreasing after 0. Now that little doodle there tells me I'm getting a maximum. So my conclusion then would be g, not f, g, has a relative max at, did they ask for the coordinates or the x where this happens? They said find the x where this happens. So at x equals 0. Why? Because g prime changes from positive to negative there. In my mind, that means g went increasing to decreasing there. But it's the first derivative test, so we use the first derivative for our justification. It's not the g increasing, decreasing test. It's the first derivative test. Just to verify, I hope that you know what the graph of this looks like. If I replace g with y equals root 4 minus x squared, this should, with a little work, be a well-known graph. We know that this is a circle, but only the top half because it's a positive y value for the root only. So if the top half of a circle centered at the origin with a radius of 2 is graphed, would it make sense that we have a max at x equals 0? And yeah. And it makes sense that the derivative is positive before and negative after. So all that's logical, and the chain rule helped us get there with the derivative. That is the idea on the chain rule. I hope this video was informative. Ask me questions in 7th hour. If you're not sure what's going on, have a nice day.